All right, this is a short video compared to the last one. I was trying to put it all together in one video for the whole chapter, but I kind of ran out of steam on that one. So just a couple more slides here. This deals with formal charge. So once you have your Lewis structures, then you want, you can come up with structures that may or may not actually be the correct answer. They may not be real. So if you with a certain formula, you went to the stockroom and said, let me have this. It might not be what you think it is. So formal charge, excuse me, helps you to figure that out. All right, it's a little bit tedious, but I'll walk you through it here. So formal charge is the difference. It's going to be the difference between the number of valence electrons on a free atom. So for oxygen, it would be 6, right? And the number of valence electrons assigned to the molecule. So that has to do with when it's bonded. You'll see what we mean. And you want to make sure that the difference between those two numbers is small. And if that's the case, then the molecule will be stable. The structure that you propose will be stable. All right, here are the rules. We'll start with the first three. All lone pairs are assigned to the atom on which they're found. Half of the bonding electrons are assigned to each atom in the bond. The sum of the formal charges must equal the molecule's overall charge, which is 0 for molecules, and the ionic charge for the ion. And you put all that together, your formal charge is going to be the number of valence electrons minus, now when it's bond, so this is when it's just by itself, just the element. Now when it's bonded, we're going to look at the number of lone pair electrons plus half the electrons in the bonds. And we're going to add those together and subtract that from the valence electrons and try to get a small number. So smaller formal charges are favored over the larger ones, and we'll worry about the next two rules in a minute there. Okay, so we're going to start with rules here. You've got the sum of the formal charges must equal the molecule's overall charge, which in our case was 0 for both of them. And then the next thing we're going to look at, smaller formal charges are favored over larger ones. So go back. Let's see what's on the next slide. So we want to calculate the formal charges for these guys. We'll start with Cl2O. And so it could be that it's ClClO or it could be ClOCl. We do not know. So we're going to write out the structures of both and then calculate the formal charges. And from that, we'll be able to decide which one is the most stable and which is the correct form that the molecule is in. All right, so then, ClO? Yeah. If you go back and look at the now, back it was ONN. So this one, if you count it out, I'll show you, you're going to have double, double, single, triple, triple, single. And the instructions for these problems are the molecule is going to be linear and keep the order of the atoms the same, oxygen, nitrogen, nitrogen, like that. Here we go. All right, we're going to look at, oops, what was this? Okay, so ClO versus ClOCl. So then, actually we need to get the lone pair electrons and everything. So if we were going to write out the Lewis structure for the one on the left here, you got 2 times 7 for chlorine plus 6 for oxygen, so that's 20 electrons. So we got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. And similarly, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. All right, now I'm going to make a list. This will be the first chlorine on the left. This will be the chlorine in the middle, and then it'll be the oxygen on the right-hand side. Calculate the formal charge for each one. So it's going to be 7 by itself minus the number of lone pair electrons, which is going to be 2, 4, 6. I'm doing 2, 4, 6 right there. And then we're going to add 1/2 the number of electrons that are in the bond. So there's 1/2, whoops, times 2 electrons in the bond. So that's 6 plus 1. So the formal charge is 0 for the chlorine. And we can just write it on top. All right, the next one is chlorine by itself is 7 again. This time we have 4 lone pair electrons. So that's going to be 4 plus 1/2 times the electrons that are in the bond. We got 2 electrons here and 2 electrons here. So it's the ones that are connected to the chlorine. So that's a total of 4. So this is going to be 4 plus 2 is 6. 7 minus 6 is plus 1. And then for the oxygen, there's 6 valence electrons on it. And there are 6 lone pair electrons, the oxygen. And then there's 1 single bond that contains 2 electrons. So we're going to have 6 minus 7 is equal to -1. All right, now one of the rules said that the sum of the formal charges has to equal to the overall charge. In this case, this is a neutral molecule, so the sum here is equal to 0. Now this is a check to make sure that you haven't made any mistakes. It should be 0 because the molecule is neutral. But also, the goal is not, the goal is not to get 0. The goal is to figure out what these numbers are, 0, 0, 1, and -1. So anyway, okay, so then the second one we have Cl, O, and Cl. And the one on the left, you have 7 minus 6 lone pair electrons plus 1/2 the electron. So 6 lone pair electrons minus 1/2 2. There's 2 electrons in that bond. So this is 7 minus 7 is 0. The one in the end will be the same. And the one in the middle is oxygen. So that's 6 valence electrons. And when it's bonded, you have 4 lone pair electrons plus 1/2 times. So you're looking at this bond and that one. They each contain 2. So this is going to be 4. So 6 minus 6 is equal to 0. So one of the rules, and these are the smaller formal charges. So you have 0, 0, and 0. So zeros are smaller than zeros and ones. So the answer is that this is going to be the preferred structure. And that adds up to 0, of course. So this one is the preferred structure. So you go to the stock room and you ask for dichloro, what's that one called? Cl2O, dichloroxide. And they'll give you this one. They'll give you this one right here. The other one, not so much. The other one doesn't exist, I don't think. Okay, and then the next one is ONN. And this one can have 3 structures. You have 6 from the oxygen plus 2 times 5 for nitrogen, so it's 16 electrons total. You would be given that it's a linear molecule, and you want to keep the order the same, the order of the atoms the same. Okay, so we got that, and there's 3 possibilities: ONN, ONN, and ONN. Excuse me. You'd have to work out the details here, but you can get octets for all the atoms involved, and you would end up with one of them being this structure. The next one would be triple, and then single. So it should be 2, 4, 6, 8, 10, 12, 14, 16 electrons. And then the other one, didn't give myself enough room there, but single, triple. And you got 1, 2, no, back up on that one, put it over here, and then 1, 2, 3 sets. So 6, 8, 10, 12, 14, 16 electrons, and that one is not there. All right, so we're going to list them vertically. Oxygen on the left, nitrogen in the middle, nitrogen on the right. And we'll say 6 number of valence electrons minus 4 plus 1/2 times, and here we're looking at 4 electrons in the bond. So that's going to be 4, that's going to be 0. The next one, nitrogen in the middle, is 5 by itself. It has 0 lone pairs. So we got 0 lone pairs, but you got 2, 4, 6, 8 electrons in the bond. So 1/2 times 8. And this is going to be plus 1. Nitrogen on the right is 5 minus. You got 4 4 lone pair electrons. And then 1/2 times, you got, in this case, 4 electrons in the bond right there. So that'll be 4, and this will end up being -1. Then you have oxygen, nitrogen, and nitrogen. Similarly, you got 6 minus 2 plus 6. I'm sorry, 1/2 times 6. And that is going to be 5, so that'll be plus 1. This nitrogen in the middle, 5 by itself, 0 lone pairs, 1/2, the total of 8 there. So this is going to be 5 minus 4 plus 1. And then you got nitrogen 5 by itself minus 6 lone pair electrons plus 1/2 times that little tiny bond there. Hard to see right there. There's 2. So 7, this is equal to -2. And then for this set, you got oxygen, nitrogen, nitrogen. 6 minus 6 plus 1/2 times 2 is equal to -1. Nitrogen is 5 minus 0 plus 1/2 times 2, 4, 6, 8 electrons for bonding. So this is going to be equal to plus 1 and equal to plus 1. And then the last one, actually I could just move that over there. Clean that up a little bit. Plus 1, and then nitrogen 5 by itself, the one on the right, 2 lone pair electrons plus 1/2 times 6, and that'll be 4 plus 8, so that's subtracting, so that'll be equal to 0. Is that right? Yeah, 0. Okay. Okay, so you can put it on top. You got 0 plus 1 minus 1 plus 1 plus 1 and -2, and then you got -1 plus 1 and 0. All right, so you go back to the rule that says, it's rule 4, and what it says is that the negative charge will reside on the more electronegative element. So there's that. And then also you got the rule that smaller formal charges are favored over larger. So we're going to rule this one out because 2s and 1s are larger than 1s and 0s. Then we're going to rule out this one because, so the one on the left is 0, 1, -1, and the one on the right is -1, plus 1, and 0. So you've got, if you remember the periodic table, you got carbon, nitrogen, oxygen, fluorine. Fluorine being the, remember the electronegativity is going that direction. So oxygen's more electronegative than nitrogen, and that's what we're talking about here. The negative charge resides on the more electronegative element as opposed to this. So it's on oxygen on the right and nitrogen on the left. Therefore, that's going to be the preferred structure. All right, then the next one was PCl3. So PCl3, you have 5 plus 3 times 7, 26 electrons. So there's going to be two ways you can draw this one. One is with phosphorus in the middle, and you're going to get phosphorus has 1, 2, 3, 4, 5, and you can make bonds to chlorine. And so it'll look like that, something like that. Okay, so then what's the formal charge on these? So the phosphorus by itself is 5, and then you're subtracting 2 lone pair electrons plus 1/2. It's got 3 single bonds, so that's 6. And that's going to be 3, 5, so that's going to be 0. And the chlorine by itself, they're all the same. 7 minus 6 plus 1/2 times 2, 4, 6. I get that right? No, I got that wrong. Well, that's right. Okay, 6 lone pair electrons plus 1/2. It's got 1 bond with 2 electrons in it. So it's 7, so it's 0. So we're going to find it's 0 on each one of these. Okay, versus this other structure, which would be, we could write it as Cl, P, Cl, Cl, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So it's another structure, right, that works in terms of the Lewis structure. So if you go through the same thing, you're going to find that the formal charge chlorine on the left is going to be 0. The phosphorus in the middle is going to be -1. The chlorine in the middle will be +1, and the chlorine on the end will be 0. So the answer is this one, preferred structure, because you have all zeros versus ones and zeros. Okay, then the next example is sulfuric acid. And if you go through this one, you could come up with 2 Lewis structures. And this is going to be 2 times 1 plus 6 for sulfur plus 4 times 6 for oxygen. So that was 30, that's 32, right? So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So that's one of them. And then you can make double bonds. So 2, 4, 6, 8, 10, 12, 14, 16 there. 18, 20, 22, 24, 26, 28, 30, 32. So you got octets again, except for the sulfur. The sulfur in the middle has got 12 electrons. Remember, it's in period 3, so it can have greater than 8. And if you go through, I'm not going to do the whole thing for you, but this sulfur here is +2. The oxygens are -1 and -1, and the rest of them are 0. On the one on the right, they're all 0. So it ends up being this one is the preferred structure. And that is borne out by experiment. So if you take sulfuric acid and take an infrared spectrum of it, you will find evidence for double bonds in the molecule. So it makes sense. All right, now I just want to show you one more thing. 2 more things. And the next one is going back and looking again at, let's see, the ONN. There we go. There we go. All right, so one more here. can't remember how I don't want to scroll back, but we had O, N, N, O, I believe we had triple, single, and then single, triple. I'm not sure if pardon me if I got them mixed up, the two on the right, but just look at the structure and then you'll have the answers. So let me put in the lone pairs. Okay, and like that. I'm going to show you here the circle method. So if you draw a circle halfway through the double bond, and what you want to do here is you have 6 valence electrons, 6 just by itself, and then you want to subtract the number of electrons that are in the circle. So you got 2, 4, and half of this 4 electron double bond is 2. 2 are inside the circle, so you have 6 for that one. Then the nitrogen, let's do the same thing, cut the bonds in half. You have 5 minus the number of electrons that are inside the circle. You got half of a double bond, that's 2, and you have 2 of those, so it's 4. So that's plus 1. And then this one, nitrogen, 5 by itself, minus 2, 4, 6 electrons inside the circle, so it's negative 1. So you get 0, plus 1, negative 1. All right, for the next one, you cut your triple bond in half, so there's 3 on the inside, 3 on the outside. So oxygen by itself is 6. You're subtracting a total of 5 inside the circle, so that's going to be plus 1. Nitrogen here. Five minus, there are 2, 3, 4, 5, 6, no, that can't be right. I've got a mistake here. There are no lone pairs on that one. Oh, I can't get rid of them. Sorry. Oxygen, nitrogen, nitrogen. Making a mess. That's a triple bond. Okay, so it's 5 for the nitrogen by itself, and there's going to be 3, 4 inside the circle. So this is going to be plus 1. And then on this side, you've got 5 by itself, and you've got 7 inside the circle. Negative 2. That's one we're going to rule out, right? Then the one on the left here, so you've got 6 minus 2, 4, 6, 7. 6 minus 7 is negative 1. You've got 5 minus 4 is plus 1. And then you've got 6 minus 3 plus 2 is 5. So that's made a mistake here. Oh, I know. It's I'm tired. Sorry. This is nitrogen here. You're sitting there watching me make mistakes, right? All right, so that last one is 5 for the nitrogen. Minus 5 is 0, so this adds up to 0. Same thing. And then what did we finally decide? That the negative 1 on the oxygen is preferred. So this is the correct structure. All right, that's the circle method. That's what they use in organic chemistry all the time. So when you take that class, you'll be using that method. It's easier. I like it. You can use it if you want to use it. Just make sure you draw your molecules right. And good, go for it. Okay, one more slide, and that is this one. Not that one. That one you can just practice on your own. This last one here is the isomers. So isomers have the same formula, but they have different, same molecular formula, but they have different structural formulas. And the formal charges are going to be the same. There's no difference between them. And so all of the forms are stable. This molecule, if you looked at HC2, H3O2, you might recognize that that's acetic acid. And then there's another molecule. It's a completely different molecule that has the exact same formula. And there's a hydrogen here. Let's do that in black. Sorry about that. Okay, so C2H4O2. And then you have the lone pairs. All right, if you go through this, you're going to see that they all have 0 for the formal charge. And you can do the hydrogens as well. So there's no real difference in terms of stability. One is not more stable to the other. The molecule on the left is called acetic acid. The molecule on the right is methyl formate. And you go to the stockroom and ask for acetic acid. You're going to get that. You go and you ask for methyl formate, and you're going to get that one. So that's kind of the idea of the ice. Those are two isomers that have the same molecular formula. All right, we're done. Sorry about some of my mistakes here. Pretty tired late at night, and I'm done. Good night.